Right, so the question is, there is a dictionary containing words from an alien language for which we don't know the ordering of the alphabets. Write a method to find the correct order of the alphabets in the alien language. It is given that the input is a valid dictionary and there exists an ordering in its alphabets. Right. So these are the words that are given. And in the explanation, we are told that the words are sorted lexicographically. So that part I think is important. So if the orders are sorted lexicographically, let's see. So we have BA, BC, AC, and CAB, right? So let's take two words at a time. So if we take BA and BC, B and B are common, but because all the words are sorted and BA comes before BC, it must mean that the B and BC were sorted based on A and C, right? Because B is the same and it wasn't sorted based on B. So we cannot conclude anything about B, but for A and C, we know that A comes before C. Let's take the next two. So between BC and AC. So right off the bat, we see that the first character B and A are different. So by the same logic, we know that B comes before A. And then we have AC and CAB. Again, right off the bat, we see that the first character is different. And we say A comes before C, which we had already established before, right? In the first one, we saw that we know that A comes before C. Right, so that's all the words we had. In case it's still kind of confusing what this comes before logic means. So what it's essentially is asking, the question is asking is to reverse engineer the order of alphabets. So typically, if we have two words, like let's say apple and ape, right? And we were asked to sort these two words lexicographically in increasing order. We would see that AP are the same, so we can't sort based on those. Then we would see P and E, and we know that E comes before P, right? In the uh, English letter. So then we would say that okay, ape should come before apple. It's pretty obvious, and it's pretty obvious because we know the ordering of the English letters. The question is saying that you have apple and ape, but you don't know the ordering of the English letters. So find the ordering of the English letters. So we're looking at the words, we're trying to reverse engineer into figuring out the ABCD and in what order the ABCD comes in the alien language. Okay, so we know A comes before C, B comes before A. You can ignore the last one because it's saying the same thing as the first one. Right, so we can say that C has a dependency on A, right? So if we were to write C, then we should write A first, if we want the words to be sorted, of course. And similarly, we have another dependency. We say that A has a dependency on B, right? Which means that if we were to write these characters in a sorted order, we have to first write B, and then we can write A. So from that, like intuitively, the ordering is pretty obvious, right? Because we cannot write A in a sorted order if we write B. So B will come first. And we cannot write C before we write A. So A would come second and then C would come at the last. But for the purpose of the algorithm, how can we represent this? copy those here. So one way to approach these kind of questions where, before we get to that, let's talk about how we can represent this in terms of a data structure. So we say that there is a dependency, or so let's say we are ordering, right? And a dependency, whenever I say dependency, what I mean is that the dependency shows up if we want to order these characters in increasing order. So when I say dependency, I mean if we are to write these characters in increasing order, what would be the dependency, right? So that's my definition of dependency. That's all it means. We can write it in any order, but because we want to write it in increasing order, how can we write it? What would be a dependency? Which character would we definitely have to write so that um, all the characters when written has an increasing order to it? And that's exactly what the question is asking for, by the way. Excuse me. All right, cool. Now that we established that. Now, based on that definition of dependency, we see that C has a dependency on A, right? Because we know that we know from the first, I think the first one, right? Yeah, we know from the first one that A comes before C. So if we were to write C, we have to write A. As simple as that, right? So let's see. Let's try it as a graph, because all these dependencies actually is easy to implement and visualize in the form of a graph. So let's say we have two vertices, C and A, right? And we say, actually we also need B, right? So 3 characters, let's put B here as well. So we say A has a dependency, C needs A to uh, to be written in the sorted order, right? So that means A needs to go to C, and similarly here B needs to go to A. Now one could ask here, why is C not going into A? Like all the while we have been talking that, hey, C has a dependency on A, and A needs to be written first before C can be written. So why is A going into C? And the reason is ultimately we want the ordering to be in increasing order, ascending order, right? Ascending order of characters, not descending order. We could do the reverse, but then we just get the reverse order, which is also a valid solution. We can have create the reverse order and then reverse it again. But because we want it in increasing order, we are kind of doing it this way. All right, so now it's kind of obvious, right? So once we represent it as a graph, this, if we follow and we follow the edges, then we get the sorted order basically. So we have to start at a node that has no incoming edges, which means that that must be the first character, right? Because if there were an incoming edge, it could mean one of two things. First thing, it could mean that it's not the starting vertex, like A or C. Another thing it could mean is that the sorting order is messed up. So if we screw up the sorting order and create a cycle, then there would be no vertex with no incoming edges. So for instance, to illustrate that, let's say in that example, we also have something like CB, right? So once we have CB, then that would create another edge here, right? And in that case, there is no single vertex with or no vertex literally with zero incoming edges, which means that we don't know where to start, right? We can start at B, but then we would come but we can't call B to be the first character or first character in the alien language because B comes after C, right? Similarly for A and similarly for C. So this is invalid. So there is a cycle, this is invalid. We don't know the sequence at that point. The other could be that, let's say we have something like DA, right? So that would mean that we would have another node here that would go all the way up to A. Now we have a predicament here, right? So either B can be the first or D can be the first. We don't know, right? And typically, like if we look at the English characters, we are never confused whether A comes first or B comes first, right? There is always one first character ever in the character set. So in this case also, it's kind of ambiguous what it is, and we can't find a solution. But fortunately, we are told that those kind of things will never happen, so we don't care. All right, cool. So now we have the graph. Now this looks very, 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 very similar to uh, a BFS or DFS, whatever you want to use, right, for graph traversal. But there could be complications. Let's see if we can find some of those complications in these examples. All right, let's take another example and see if it comes out to be as simple as the other one. So say this one, right? So we got CAB, we got CAB, we got AAA, and we got AB. So from the first two we know that C and A, right? From the second two we know A and B, right? So if we draw a graph, let's copy that and see. I haven't done this example before, so that's why I don't know if any of the examples actually brings up any of the complications. So I'm going through them. It doesn't, we can always go and create an example and try to bring up the complication. But let's see if it does. CA, AB. Okay, so this one does not. So this seems also fairly straightforward. Okay, let's try the other one. So here we have YWX, WZ, XWW, XZ, ZYY, and this one, right? ZWZ. Cool. So we know that Y and W becomes a pair, W and X becomes a pair, then W and Z becomes a pair, then X and Z becomes a pair, and then Y and W is already a pair. Okay, so these are the pairs. How many vertices we have? Y, W, X and Z, right? So Y, W, X and Z. Okay, all represented. Cool. Let's see. All right, let's see. So we have Y, W, X, Z, right? And we have edges from Y to W and W to X, W to Z, and X to Z, right? Cool. So what would be the ordering here? So we'll start with y because there are no incoming edges. So y w, and then we I think this example kind of shows that shows at least one of the complications I was talking about. So if we notice, so we start with y, that's pretty obvious. Then we'll go into w. Now in w, we have two options. We can go into x or we can go into z. But which one to go into, right? Uh, and this would be even more complicated if, for instance, this arrow or this edge was flipped. If this edge was flipped, now still we can go into both x and z, but which one should we go into? And this brings the question into the realm of topological sorting, because topological sorting conceptually says that it will sort based on sources, right? So whenever it finds new sources as it's traversing through the graph, uh, the, the sources would, in the order they appear, will appear in the final answer, right? So it's possible to do this question with BFS or DFS up to a certain point, but once we start having edges where, or certain vertices where there are multiple incoming edges, then it gets kind of tricky because you have to keep track of when those edges would disappear, and if we're doing that, essentially we're topologically sorting it. Cool. So let's see how we can solve this using topological sort. So we'll take the third example. It's kind of a little bit more complicated than the other two. All right. So basics of topological sorting is that we have to first see. Um, we always use sources when we are putting things into our result. We only put sources in our result. We do not literally do not put any other nodes, right? So we'll first say, okay, let's take a result variable. Right. So we first say, okay, we are starting with y as the only source here, right? So again, the check, right? So if we have more than one source, that's a problem. It cannot be sorted. Um, so we should throw an error or return null or whatever we want to do in that event. So that's one check we need to do. But fortunately, the question says those kind of things won't happen. But if the question didn't say so, that might be a good check to have, that if we have more than one source to start with, it's a problem. We won't have a sorted order of characters in that case, because there will always be a ambiguity or confusion between which source to pick first. All right, cool. So first we put in y, right? And then we go on to w. Put in y. So now because we have put in y, this y is gone, right? So when I say gone, what do I exactly mean scientifically? So we're going to keep track of something called in-degrees. And in-degrees are essentially the number of incoming edges to that particular node. And we would call a node as a source, right? We would call a node as a source when the in-degrees is 0. So our starting source is y in that case. So here w in-degrees would be 1. In x, that would be 1 as well, I think. And in z, that would be 2. And why is this important? And why do we care about putting this in degrees? Because that gives us the order in which it would appear. So remember, we're talking about from w, which one we should go first, x or z. X is the only answer here, really, because we cannot use z, right? Because if we say w and z, that's an invalid order. That would tell us that z comes before x, which it doesn't. It clearly says here that x comes before z. So that's a contradiction. So we cannot print z before x. And the in-degrees would prevent us from doing that, because as we go further on the example, we'll see that unless the in-degrees become 0, we do not consider it a source and we'll never print it. So that's, I think, one of the advantages we have using topological sort in this kind of questions versus using just vanilla BFS or DFS. I mean, we are still going to use BFS as a traversal method, but we'll add in all this topological sort logic in there. Cool. All right. So yeah, so we find integer 0, y. So this is the source. So what we'll do is we'll put the source in the result and we'll remove the source. So this no longer exists in our mind. Now, as soon as we remove it, the integers of both w and x, the integers of w become 0, right? So w is the new source now. So now we are going to put w in the result set, right? And as soon as we remove w, then the integers of these nodes also reduces, right? So this reduces to 0, this reduces to 1. Now this is the interesting part, right? Both of these had connections from W, but because Z has had a connection from X, it integrates is still 1, which means it's not a source yet, but X is a source. So we will add X to the result. And since we've used it as a source, we'll remove it. Now the integers to Z becomes 0, so now Z becomes a source as well. So we'll remove that and add Z to the result set. And when we're done sorting, we'll get YWXZ as our result, which is what we would expect out of it. So that's pretty much what the algorithm is for this kind of question. So what's the time complexity? So the time complexity is that we visit every vertex and we visit every edge, right? So it's linear based on the number of vertices and edges. So it's V plus E, which we can simplify and say it's the number of V's, number of vertices. Space complexity, depending on which traversal method we pick to use, we would use either a stack or a queue. If we are using a queue, then in the worst case scenario, we will have n or v minus 1 vertices in the queue, because let's say we had a weird graph, something like this, say A, and then B and C, right? So this is the worst kind of graph that can exist for this question, for in terms of the space complexity. And it's bad because except this one source, all the other vertices are, so once you remove this one source, all the other vertices will become sources themselves, which means all of them will end up in the queue, right? So it's v minus 1, so total v's are 3, so 2 v's here would end up in the queue. So v minus 1 or v would be the space complexity here. All right, cool. Now with the time and space complexity, we went through some examples. Let's see if you can code this out. Cool. So, right. So first we need to create. The most important thing here is to create the edges, right? So we'll have set edges. Let's create a list. It's easier because we don't know how many edges would be there yet. Right. And then we have to count the number of vertices there are. Okay. Now we got a list of words, and if there are no words, then there's nothing to sort really. Okay, so our logic was that we will go through the words and then go through the characters and see and uh, create that edge relationship, right? So let's pick two characters at a time and try and do that edge relationship. Two words at a time, not characters. Right. Now, if the number of words were 1, then that could be a problem, right? But let's see what happens if the number of words were 1. I mean, we could infer there that, say for instance, we just had YWX, right? We could infer that y comes before w and w comes before x. That could be an inference that we make. The problem with that inference is that we have nothing to verify that against, right? I mean, we can always assume that, what they've given us is correct, but it's unlikely that they will have an input like that because it's only a guess at that point that y comes before w comes before x, and if we make the assumption that this is correct, then really our order is that, right? YWX. So yeah, if we get just one string, we can just return it, assuming that whatever you have given us is the correct thing. I have no way to verify it, so we don't know how to process it. Okay, so till here, now we can safely say that, yeah, there'll be at least 2 words in this array. So we can take 2 words at a time. Okay, let's do that. Character here, not edges, not integers. Cool. So let's see how the comparison is working here. So here, if we have 3 words, then we say and they will be indexed 0 index, right? So 0, 1, and 2. So one thing we can do is that we take whatever index I is at plus 1. So that would make us compare 0 and 1. Then when we move to 1, we'll take plus 1 and compare 1 and 2. And to 2, then we do a plus 1, but that is more than the number of words we have, right? So at that point, we can just ignore that one because, obviously, we can't compare. Another thing we can do is we can actually go up to -1. So border length is 3. So if we go up to 2, so we get 0 plus 1, 1, 1 plus 1, 2. So once we hit 2, we stop. So I can just do this. All right, cool. So we have the first word. Right. So logic was that we will keep on comparing until the characters are unequal, and as soon as we find an unequal character, we're going to put the relationship in the edges. Okay, so we'll do this till we get to a set of characters that do not match, at which point we can say we can populate our edges, essentially. So yeah, okay. So that would give us the edges, but we also need to compute the vertices. Um, right. One more thing we have missed here is that if if the edges already exist and was found as part of a different word, we don't want to capture that either, but we can take care of that after this actually. Let me think, even if they do exist, does it actually, yeah, I think we should, yeah, we can take care of those after. All right, and of course we need to increment our vertices as well. Okay. Okay, so what I'm thinking, we can do another set of optimizations here. Maybe we don't have to do this separately. Let's see if we can do it together. So let's talk about the graph, right? So let's initialize the graph. So let's initialize the integers first. And let's initialize the adjacency of the graph itself, which we would represent using adjacency lists. So that's our integration graph maps. Now let's fill that up with the nodes. Okay, so now both these maps should have the nodes in them, or the vertices in them. Let's see, why is it failing? None in 104. Okay, cool. So now our life becomes a little simpler. So what we need to do, we actually don't even need these anymore. So what we need to do is that we have to keep comparing, and any point we find different characters, then we uh, add that as an edge, basically. Right. Okay, so now once we found that different characters, we can break out of this loop, because we really don't want to go through all characters and do this, right? Because we just want to find the first point at which these two words were sorted. Okay, now let's see. All right, so now we have the graph and we have the integers. Now we have to do our actual sorting. And at the end of the sorting, we are going to store that in a string to represent the sorted order of the characters. So we're going to create a string builder to represent that result. And I'm going to return this. Now for the actual sorting, we are going to use BFS as the traversal method. So let's take a queue. And this queue actually just represents the sources. And why is that? So the reason being that we only consider the sources to be put into the result list And also we only consider the sources to find the edges, right? So we don't randomly go into an edge and try to figure out its children. We only take the sources and figure out their children and then go on from there. The reason being that, let's say we randomly go into Z and try to figure out its children. We won't find any children, but depending on how we arrived at Z, Z may be at a different order from the previous example where we saw that if we remove W, then it must print X after instead of Z. So let's do that. Now we're going to populate the sources queue with just the sources that we have currently available, and we can find that from the integer. Sources are essentially vertices that do not have any integers. And then we're going to start our traversal. Now, here in the traversal, we are going to pull out a source, and let's call it parent source. I don't know, something. Come on. Okay, so now that we have a source, we can add that to our result. And we can, we need to get all its children, right? So um, and for each of these children, we'll take a child and we will decrement its in degree. And we're decrementing because we are sort of deleting these nodes, right? So if we delete y, for instance, then the number of integers reduces for both for w. And if we remove w, for instance, the number of integers reduces for both z and x. Okay, so now that would offer the child back into the sources queue. It will keep on doing that and reducing the integers as we go along. So that should be about it. Let's try and run it and see where it fails. Null pointer exception, blah, blah, fails on line 111. So here, right? So it's failing. So why is it failing here? It's creating a null pointer exception. I wonder if it's spelling at the filtered step or the for each step. Okay, seems like it's spelling at the for each step from the step trace. So guessing this entry is coming out to be null. So maybe a good thing to print out would be the in degrees itself. So let's do that. Okay, so is E null, B0, C null. So the integers are not being populated properly. Right. It's kind of weird that it's actually doing null, right? Okay, let's see. So every degree we put the characters, we assign 0 to it. So this, why is A not getting assigned 0? And also it's kind of messed up, right? Because it's not. Um, it doesn't actually have the counts, it seems. Okay, so in degree definitely is not getting populated like populated in a way we wish it should. Hmm. Interesting. Yeah, we at least know the keys are right, ABC, right? It's the values that are messed up. So what's screwing up the values? I think I might have screwed up this thing. Got an extra one here. Let's see how this goes. Okay, so at least now it's not failing there. You got a B as the 0 as it should. Um, what else? Right. So now let's see. The result we are getting is wrong though, I think. So character order we are just getting B, which is the first one, but nothing after that. And ah, sorry. So this should be -1, right? So because we're taking out an integer, not adding one. Right. So BSC, CAB, this one, see if that matches. First one is BSC, second one is CAB, third one is WIXL. Cool. Yeah, so I think that's the whole alien dictionary deal. Just to recap, the whole logic of the problem is that based on the words we are given, we need to find the vertices, which are fairly simple because it's just the characters. Those would be the vertices. But what's more important is this ordering between the characters, right? So because this is sorted, we'll use that property to find that ordering between the characters and create our edges. Once we have the vertices and the edges, it's just a simple topological sort. Yeah, and that's about it.